All right, well, thanks everyone for being here. So we'll get started right away. So today I'm talking about improving introductory computer science education with this mystery DRaCO. I'll explain what that is in a bit. But before I begin, I just want to acknowledge everyone. Thank everyone for being here. Of course, my parents-in-law are not here, but their support and love. My sister Joy is here. My wife Jessica's back there. Thank you for everything you have done for me. And then the friends, Toby, Vivian, and other friends, Chris. Please know that I really appreciate your friendship. And I wouldn't have been here if it wasn't for your support, all of you. And of course, the teachers I love so dearly. Thank you again for being patient with me all this time so that I could get here. Thank you. All right, so let me just go over really quickly what I'm going to be going over. So I'm going to introduce you to my work, and then I'm going to talk about some related work to put my work in context, and I'm going to talk about some background and some keyword that you're going to need to know to be able to understand what I'm talking about. And then I'm going to propose a new teaching method that uses the DRaCO. And I'm going to show you what I did to validate the teaching method, see how effective it was. And then we're going to talk about results and discussion on how can we go further. And at the end, I'm going to conclude and point out a couple things, addressability and future work for anyone who wants to continue my work. So let's go ahead and jump into the introduction. So I had this motivating example. So let's say that we are putting together a party guest list, just like the one we're having right now. And let's say there are some names on here, and let's assume that none of our friends have a same name, so Mike, Jess, Joy, Jess, and John. And if we ask this question, did we include someone's name more than once by accident? Maybe because we love that person so much. Maybe if you ask this to fifth graders, I observed that they usually don't have much trouble explaining, oh yeah, maybe we'll look at one name, and then we're going to see if that name appears anywhere else on this party guest list. But if you ask the same question to someone in CS1 course, the Introductory Computer Science course, what I have observed over many years is that they have very difficult time trying to come up with an answer, and they something like, maybe I'll write some code, like start with this, okay, I'm gonna open up an editor, let's try and type in some code, oh, oops, I forget how this piece of code works. So they just kind of get bogged down right there. Although this is something you can intuitively kind of think about without having to write any code, and even if we ask a question like this, without asking them to code anything out. So maybe that phenomenon can be understood a little better if we put this into context. So let's take a look at the workflow of a fifth grader and a workflow of a beginning CS student. So maybe the fifth grader just write these names down and use a pencil to go through what's given, this data. But for a CS student, their context is working with a computer system, with the syntax of a language they're learning, right? So maybe what really matters, the problem itself, kind of becomes a second priority to what they're trying to do, which is understandable. They're trying to learn how to program, so they want to practice programming. But still, kind of the point where we want students to think, okay, how can we approach this algorithmically? What are our intuitions? Is the intuition useful? And things like that gets a little forgotten sometimes. So I'm going to quickly talk about this work by Sally Fincher. What are we doing when we teach programming? I understand that this work is a bit problematic, and it's a little old, and also it has some statements that are not 100% agreeable, but because I saw this paper and really it inspired me to do the work I'm doing, I'm just going to point it out, paraphrase what she's saying, and then we're going to move on. Okay. So what she says in this paper is before, when computer science was just about to emerge as a field, scientists learned to program. Not because they were particularly interested in all the complexities of computing and the programming, all the discipline that goes into it, but because they wanted to solve a problem, scientific mathematical problem. So they didn't particularly care about the programming as a discipline, but that's certainly not the case in today's classroom when we teach computer science. So now that the programming is its own discipline, teaching it just like the way those scientists and mathematicians learned is maybe limiting. And the reason why she says it's limiting is because students, like I said, get bogged down in the specifics of the syntax. So, and this line is where I draw the inspiration from, although I find that the statements above it may not be 100% agreeable. Okay, so now from that, I'm gonna talk about some questions I want to address. One is, what are some existing alternatives to teaching method that let students get bogged down by syntax? And two, what are some existing methods and what are they lacking? Why is it that if there are some existing alternative methods, they're not being used everywhere to help students not get stuck? So if there are some things that are lacking in the existing methods, can we do something better? Can we copy something better such that we can help students make the CS1, the Introductory Computer Science course, more effective? And lastly, how good is the method that we come up with? And that's where we do the validation. So that was the introduction, so we can move on to some related work now. So I'm going to bring up that paper again just because she mentions a couple things. And in this particular paper, again, what we are doing when we're programming, she introduces the syntax-free pedagogy, and it's not really syntax-free, although that's what she calls it, so I'm going to stick with that terminology there. And there are two books that gets introduced, and one is by Richard Bornat that uses ISWIM. It's a kind of a pseudo language which later on got embodied as ML. If you see what I mean is what this is an acronym of. And this book teaches students to start with some pseudo-language, i.e. ISWIM, write out their algorithm, paper, pencil, and then once they have it done, the algorithmic thinking done, then move on to some concrete languages like Pascal, COBOL, Algo 60, and Ada. Again, it's a pretty old book there. And then Russell Shackelford, another one, Introduction to Computing and Algorithms, has a similar method that uses pseudocode, again, pencil-paper approach, and then moves on to more concrete formal languages. So that was one set of existing methodologies where we introduced some pseudo-languages so that students can kind of not worry about the computers for a bit, not worry about dealing with the compilers or some evaluators, just kind of externalize the thinking, algorithmic thinking, in some structured form. And now I'm going to introduce these initial learning environments, which are pretty popular in really early computer science education from elementary all the way through in university level. So this one is Carol the Robot. This is from, I believe, 1981, and it is paired with some simple syntax in a graphical interface such that students can learn how to program by programming this robot to move around in this 2D grid. In Alice, another popular one that is based on Java, a particularly interesting feature about this one, again, it has to do with some interactive art, but it uses the drag and drop kind of a methodology and tools so that students don't have to worry about typing code incorrectly, although this is still backed by Java, right? So having some understanding of how Java syntax works is important to be able to use Alice. And this one's Greenfoot, again, backed by Java. You can see there are some classes that are being defined here, and again, paired with some interactive art going on. In Code Combat, this is pretty new compared to the ones we've seen so far. This is an online game that's based on Python, where writing scripts in Python lets the characters on the screen move and commence combat. So again, the four platforms I've shown here are all backed by some popular formal concrete languages here. And there are some other ones like Scratch, Google's Blockly, and Moana. This is a very specific example from Hour of Code activity by Disney. And these are all kind of inspired by Scratch's Blockly approach like this. So Scratch has its own syntax, yes, but each snippet of that syntax is encapsulated in this puzzle piece or Lego-like pieces so that when students drag and drop and try to put things together, only the pieces that go together, that belong together, are snapped together. So it dramatically reduces the chance of making mistakes, and ideally, it's more suitable for younger students who wouldn't really be able to type things and put things together in a traditional way. So Google's Blockly is really similar, but one thing that's different about this one is that this real-time translates this Blockly code into Python or JavaScript or some other new language. I think they also now support PHP and some others, so that students can see how to put these blocks together and what, in real life, right, later on in their academic curriculum, that code might look like. And lastly, kind of similar concept, this one is interactive art plus that Blockly paradigm put together, and this is part of the Hour of Code activity so that this concept of programming can be introduced to the younger students. Okay? So those are the three platforms, initial learning environments that uses Lego-like syntax. And now the third related work I want to look at is multilingual pedagogy, and this is specifically from UC Berkeley's CS61A course. And they teach 3 languages in a single course. Given that they are in a semester system, it's probably a little easier. They teach Scheme, Python, and SQL in the introductory course, and here's what they have to say about this. They say, our goal is not to choose what language you use in your future, but if you've learned all these languages and kind of abstracted some concepts, common concepts out of them, Our hope is that once you have learned the essence, you will find that picking up a new programming language is pretty easy. Okay, and then now I'm going to talk about some things that most or all of them are lacking. One is that computer science, early computer science education can lack this capitalization on students' existing skills. So what I mean by that is when you walk into introductory, say, calculus course, the math teacher can easily say, hey, remember all the K through 12 math education you had? Remember whatever the last course you took in high school? Right? We can directly, the math teacher can directly refer to the course that exists prior to computer science. Of course, there are some computer science curriculum that allude to some previous courses, but it's not really easy in current K through 12 standardized education that teacher in a university setting can easily refer to a single course they know for a fact that they have taken that is discretely computer science. Right? So we need to be able to make some connections. That would be nice, but it is kind of difficult. And often if we do want to make a connection, we have to go kind of cross-disciplinary. We have to talk about math and things like that. And of course, not being able to make the connection to students' previous experiences cost cognitive load on students' end. Students think that, oh, this is a brand new thing. I never heard of this before. And a lot of teachers maybe do say that too, perhaps. This is different from what we have done before. Maybe you've never taken computer science before. This is your first computer science course and so on. So that increase of cognitive load on top of all these languages in case of multilingual pedagogy, and maybe even in the syntax-free pedagogy where students have to get used to the pseudo-language and the formal programming language. Right? So there's a lot the students need to take in and process at the time. And here, the last one is the persistence of the blank pages. So what I mean by this is that there is this concept of blank page syndrome that is coined by the Program by Design project, which teaches DRaCO how to design programs, the textbook. They say when beginning students encounter a blank page, right, something like this, I'm sure all of you have seen something like this, and they don't know exactly how to program, they feel lost, like, okay, this is an empty window, what am I going to do? And personally, this still kind of haunts me. When I'm starting a big project, I open up my IDE or editor and it's like, wow, that's blank. Where do I start? So we kind of draw this inspiration from here. So instead of letting students be confused by these, let's try and address these shortcomings and come up with something that could potentially improve the education. So that was related work, and I'm going to talk about some background that's necessary to talk about our teaching method. Number one is a design recipe from How to Design Programs, again by Program by Design project. And they define a 6-step process that starts with data definition, signature, purpose statement, and header of the function or program they're supposed to write, and the examples, which can be used as a test-driven kind of a paradigm there. And a function template, this is where students kind of lay out the basic structure of the function, and then the definition, actually filling out those templates, and testing, running the example to see if they work. So here's a quick example of this. This shows 2, 3, 4, and 5 where they have the signature. This is a rocket hires a function that's going to take in a number and generate a number or return a number. And then they're going to this is multiplying the number of seconds by 7 to find the height, is a purpose. And then there's examples for the function and the actual function definition here. Okay. So it gives a very good process for students to perhaps encounter a blank page, but know exactly what to do. If they follow these, they will have a working function or a program. And the second concept is short-term memory. This comes from cognitive science, and it's from G.A. Miller's The Magical Number 7 plus or minus 2. If you took Intro to Psych sometime recently, you might remember that in kind of a short-term memory or RAM or cache of human brain, we can only hold up to about 5 to 9 things, not necessarily just discrete objects, but number of digits and number of steps in a process. So that's kind of a key concept we're trying to embrace here, that students have the same restriction when they're in computer science course. And then outlining. So outlining comes from, again, cross-disciplinary language arts like English composition or any composition really. And what it does for us is to externalizes a writer or author or programmer's short-term memory, right? We can only hold so much in our short-term memory, so why don't we externalize them, flush the cache, right? So that we can write more things to it and just use it more versatilely, right? Without having to worry about losing some intuition. So the definition by Katie Bromley is really, it's been established pretty well in 1985. The outlining is identification of main ideas and supporting details in a specified format. And what's really good about this is that it's included in most elementary language arts and curricula, and it's often taught. The students already know this coming into the class. So we can definitely capitalize on the fact that students know this. Okay. And then I'm going to talk about a few terms that I specifically use for my work. So when I say formal programming language, I say it's a general purpose as opposed to domain specific, a Turing complete and readily available programming language with an evaluator that allows such language to be executed on a computer. So good examples of these, Java, Racket, C++, and Python are formal programming languages. And an implementation plan is a set of steps to implement a particular solution to a given problem in a manner that can be used later to compose an executable program in any formal programming language. Okay. And friction. So this will appear a little later, but just kind of giving it to you up front here. It's just a measure of difficulty in implementing a teaching method in an introductory computer programming course caused by students' emotional resistance. So if they totally hate it or it's difficult for them for the teaching method to being utilized there. And then the framework. So this is kind of a preview of what I'm proposing. So there are 5 key components in the new teaching method that we have come up with. And number 1 is the design recipe. We have our own augmented version of design recipe. And then the second one is code outlining. A third one, peer review process. So note that this is not a code review, just a peer review. And I'll talk about that a little bit. And automatic code template generation and automatic unit test generation. Okay. Lastly, ability to program is the ability for a student to adequately perform all the following tasks. Again, something I have defined to kind of narrow down the scope of what we're trying to get students to do or do better. 1, effectively decompose a problem into discrete subproblems to devise solution to the subproblems in terms of the implementation plan. And then communicate the plans of implementation to other students, devise a range of test values for the program to be implemented. And finally, follow the implementation plan they have come up with to actually write an executable program. Okay. So finally, we can talk about the new teaching method. Right. So I just want to clarify the primary goal here is improving the effectiveness of early computer science course such that participating students' ability to program I just mentioned is positively impacted such that we can quantitatively verify it. And important here, so we're not trying to say, syntax is bad. Don't use any syntax of a formal programming language. It's not at all what we're saying. We recognize that that's just impractical. Of course, students are going to eventually need to encounter them and use them if they want to go on to the industry. So that's not what we're trying to propose. Okay, so the first piece is the design recipe. Here's a quick illustration of what it looks like in our particular case. And we say it's a process of determining the name, inputs, outputs, its purpose, side effects, and example test cases of a program, and externalizing them. So they have to write it down in certain format, like this. Okay. And we also use the term design recipe to refer to the artifact of that, this textual artifact, which can be used later as documentation. And another thing that's kind of unique, I would say, about our particular implementation of design recipe is we provide students templates always. So students will never encounter a blank page. They will always have a template that's kind of asking for, okay, what's going to be your function's name? What's the inputs? What's the outputs? What's the purpose? And all these things so that they're led to fill these things out. So they know exactly what they should do first. So the prerequisite of this is, of course, we need to talk about some data types and some functions, the concept of functions, before we can introduce them design recipe as we have. And again, this template that asks students what to do addresses the blank page syndrome, because students are never going to be introduced to blank page here, because they can always bring the template and start from there instead of opening up a blank page and feeling kind of lost. And again, because we're asking very specific things about a function, it forces students to think about, okay, what are some good decomposition things to do? But they may not know what decomposition is as concretely as teachers do yet, but thinking about functions, I think, will lead them into kind of breaking up a larger program into separate discrete functions. And here, one unique thing we do is we immediately separate the function arguments from a system level I/O. This comes purely from our observation that students confuse a lot the function's input-output to the system level I/O, like printing hello to the console. That's an output through a side effect to the user, but students sometimes, and most often in the very beginning, confuse, okay, what's the difference between the output of a function and an output to the user? So we just separate that right on, early on, instead of having to talk about the side effects later on, so that students have a visual separator between the function input-output and the side effect input-output. Okay. And the last thing, our particular design recipe, although this is written in a particular format for a reason I'll discuss later, our specification of the design recipe doesn't require it to be written in any particular format. It could be handwritten, as you saw the paper form of the template before, and it could be written in some common format of some language. We mostly don't care because we want students to just fill out the form and think about the process of decomposition. Okay. So now the code outlining. So this is kind of the central piece of what we're going to have students do to be able to externalize their algorithmic intuition. So the definition here, the process of describing the implementation plan for a program, a function, or subroutine in natural language, so that's a key, in a bullet point format with optional utilization of having some nested bullet points to show some structure and organization and readability. So here's one example. This is from the Skater project of CP101, if you're familiar with it. And all students need to do is just write down what they're going to do in their program, and this is written in the Python comment syntax. So it's pretty simple, very linear, top-down. But later on, as students are introduced to more complex concepts like control structures, iteration and things, and functions, they can write these kind of nested, structured outline. So we start seeing, okay, we're going to loop through, iterate through some things. Here we are using some conditionals here. There's an else if, some here, and then again iterate through something. So it can get more complex as they learn more new concepts. And we also provide a way for students to kind of, they do their design recipe and then outline what their function is going to do. So let me talk a little bit more about the benefits of this. And first of all, there's no hurdle. Students already know exactly what outlining means. They have done it countless number of times, K through 12 education, and it externalizes the algorithmic intuition students have. So students read a project specification, a problem statement, and they think about a couple ways they might be able to approach it. But if they call up Vim or some editor to start typing right away, having to deal with or recall the syntax they're not yet familiar with might bog it down, might just totally blow away the ideas they had that hasn't been externalized yet. So once they have externalized it, it's semi-permanent. Unlike memory, it's not as prone to corruption. And what this allows students to do is students can revisit it, they can review it, they can fix it, and they can critique it. And there's plenty of opportunities for students to just use that concrete, tangible form to develop further their algorithmic intuition to something more mature, something more useful. So we package these two, design recipe and code outline, as a package, hence the name DRaCO being the acronym. So here's a recommended steps as students approach a kind of a larger problem or project. First, we say, okay, you should write the high-level code outline. Right? What is the main purpose or main objective of your program? In order to get there, what do we need to do here? And maybe students will be able to identify, okay, here's a good use for a function, here's another use for a function, and then that will kind of prompt them to design some functions with the design recipe. Right? And then from here to here, they're kind of making this concept of, okay, let's make this into a function more concrete by specifying exactly what the functions required pieces are. And then once they have written the functions, and they can go into the function level and define the code outline for those as well. So again, so we kind of provide this DRaCO as a package to students just to make it easier for students to understand, hey, it's a workflow, it's not the bunch of individual stuff you need to do. It's a process such that once you have completed it, you have a very specific concrete plan externalized onto some form. Okay. And once that's done, we can do this review process. An in-person, that's a key part here, in-person review process of the artifacts of DRaCO workflow, where the participants shall examine, discuss, and critique each other's implementation plans via verbal and written communication. And once the students have made at least one attempt at DRaCO workflow, we can begin this right away. So students begin talking about what they have done. And like I said before, it's not a code review. So whatever students have written is not lost in the syntax, right? Even if the students have written a perfectly good program, the person reviewing it and critiquing it is not as good at reading code, then the whole process of having written code for the sake of review is not going to be as great or effective. So everything's written in natural language and code outline form, as I've shown before, and it's conducted in person. I think this is important so the students can freely communicate. It's better than any electronic form, I think, so the students can ask questions. Hey, I see this here. What do you mean by that? Oh, it's just something maybe I misread, or maybe I misunderstood, or maybe it's something that the author needs to fix. Right? That communication is just immediate. And then it can be conducted informally. We can just let students talk about what they have done with the DRaCO artifacts right in front of them, or it can go more in depth. So I'll show one example of what this in-depth process might look like. So I provide a worksheet, and it asks students to particularly examine a few things. So what are some functions that do some particular things? So these are some questions that ask students to identify certain features of a program that was written out in the implementation plan. And then one question that asks, okay, look at one of the examples. What do you think that is testing for? Is that a corner case? Is this a particular case? Describe what that means. And then on the back page, we ask them to, again, talk about some outlines and also think about some corner cases. Right? Can you identify from the implementation plan how this person is thinking about some corner cases? And then at the end, we kind of ask for a comparative analysis that asks, okay, well, what was different about something that you've done and something that the original author is doing, and something that's similar? And what can you make suggestions on? Is there anything you can make suggestions on? And then the reviewer will finally make an evaluation on the implementation plan. So that's kind of the example of the in-depth process. And then throughout this whole workflow, we provide this automatic code template generation and unit test generation. And we define the template generation as a code template or stubs more widely and more vaguely. So we just say programmatic generation of some starter code, again, programmatic as in automatic, based on the student's DRaCO artifact such that the generated code may provide some guidance. It could be a lot of guidance, it could be very little guidance, depending on the instructor's preference, to the author of the DRaCO artifact on how one could start implementing their program in the syntax of a programming language. Again, this is kind of an attempt at taking away the blank page from the students. And so they have some guidance. So again, once the students have done DRaCO workflow, they can start using this. And another purpose is that it kind of dissuades students from thinking, oh, DRaCO is just extra work, I have to do all these documentation. But if the documentation generates some helpful things for them, maybe we can convince them, hey, this is actually useful, even at a superficial level to the students, because it does something. And that's the second point here. A lot of the pseudocode or pseudo-language approaches is stale. What I mean by that is students write this great work, and it's on a piece of paper, you can't feed it to the computer's never going to understand it. And you have to, as a human, transcribe every single piece you have written into code if you want to see it actually work. Right? So instead of burdening students with that, we want to give them a little advantage so that they can use the DRaCO artifact to interact with the computers. And this is an idea from scratch where we need to incite some excitement among students. And with this interactivity, we're hoping the students will find it a little more exciting than if it was just totally stale. Connected with this is unit test generation. It's more specific, programmatic generation of a working unit test suite. So it's not partial, it's not a starting code, it's a complete unit test suite that you can run right away, written in a formal programming language based on the DRaCO artifact. Okay. Again, students can start this as soon as they have the workflow artifact ready. And the big thing we are trying to get with this is that we're trying to cultivate an environment where we're telling them, hey, writing tests first is important. When we say that, the students will actually buy it instead of thinking, I don't know my test, it's too much. Because doing this, because it's automatically generated from what they have done quite simply, it requires zero knowledge of any of the unit testing framework. There are a lot of unit testing frameworks, they're great for the industry, but they kind of have a lot of overhead. You need to understand what object orientation is, what are the kind of self keyword in Python. It's kind of a mess for the early students, so we just took that out of the whole equation. And if the students put good attempts at making the DRaCO artifacts, they'll have the benefit of TDD, which is a confidence, right? They have a suite, a unit test suite they can run as soon as they have written some code, and it will either tell you that it's working great, move on, or something failed according to your tests, so it'll fix your code. So if they see that unit test bar grow into more and more green, or see OK message, then they know, right, based on their tests, that their code is working. So again, hopefully, with that benefit they experience later on when they get to the actual practice of TDD, when the teacher says, hey guys, TDD is great, it gives you confidence, they will know that that's the case. Okay, and we named this new teaching method a DRaCO-based pedagogy, not to be pompous or anything, just so that we don't keep calling it new teaching method. and because we're going to talk about different teaching methods as well. So we just, from now on, just say DRaCO-based pedagogy, and then we try to validate it now. Okay, so some background on where we have deployed this. There are 2 introductory courses at Cal Poly San Luis Obispo for the CSSC department. CP 1 to 3, which is Introduction to Computing. We try to kind of retain students and get them excited about computer science. And once they're done with that, we put them into the CP 101, the Fundamentals of Computer Science. And usually, the structure of CP 101 is like this. It has, for every week, a 3-hour lecture, and for everyone who goes to the same lecture, they are put into the same lab, so they're all kind of together most of the time. But what we have done to validate our method is we split the lab into 2, one back-to-back, one experimental, one control, so that half of the lecture group goes to one lab and the other half goes to the other lab, and that's how we split the AB. So what that does is that we have delivered them all the same material, but for the experimental group, we have delivered them little extra material regarding the DRaCO workflow. Okay. So continuing with the background, the grading scheme goes like this: 10% lab assignments, 30% projects, which are kind of bigger programming assignments, and 30% of 2 midterm exams, so 15% each, and then 25% of final exam, which has a small portion of lab final where you have to actually program, and then 5% participation. So where we have deployed the evaluation methods was into the lab portion of the final exam and then parts of the midterm exams. Okay? And quick demographics about our students. Most of them have taken CP 1 to 3, so they have some programming experience, but it's limited. So more than 50% report that they have either less than 2 months or 2 to 6 months of programming experience. And when it comes to Python, which is what CP 101 is taught in, again, more than 50% say, nope, never even seen it, with very small portion reporting that they're proficient. Okay. So with every project specification that asks us, build this program or build that program, we have included for the experimental group this particular document, design recipe and code outlines, and this is exactly what the students were given for one of the projects, and it has some instructions on how to do the DRaCO workflow. So read the pages, specification, understand what it's asking for, think carefully about the functions you're going to write, and once you have decided on the functions, write the DRaCO, and once you've completed that, for the main program, write the piece the functions together so that they're all in one piece, so that you have the high-level outline, and then turn it in. And throughout the whole process, students are also instructed to use the automatic code generation and the code template generation and unit test generation. Okay. And so here's a quick example of what I meant by we give students a template. So this is a quick clip. So we're using Sublime 3 here, and by typing DR, students were able to call up this template, and by pressing tab, they can go field by field. So you can see that the field 3 of 9, field 4 of 9, we're advancing through the field just by pressing tab, and then filling in this form that's electronic, and also in the form of a Python source code comment. So we are just writing some kind of meaningless function here, add and say hi. So we have defined 2 inputs. It's going to take 2 floats and return 1 float by adding them. And we're saying it has a side effect which shows a string. Again, to separate the input output of a function from input output of an actual program or system level. And then we write some examples. Students can describe what the examples are. And then that's the process of how to write the design recipe for just one function. Just quickly want to show that to you. And then the Dr. Cop. So design, recipe, and code outline processor. Thanks goes to Tobias Bleich there for helping me come up with this name. Yeah, it's a doctor who's going to help you, but it's also a cop who's going to whip you if you do something wrong. I don't know if it actually achieved that, but that was one suggestion there. So it handles both the code template and unit test generation. And it's available, I made it available on Cal Poly Unix machines so that they can use it as a part of their command line Unix workflow where they have to upload the files, test it there, and then they hand it in there. So it's all part of that process there. And then it takes in a function level DRaCO file, so it only processes function level outlines that end with .oln.py, oln for being short for outline. And then it generates a function stubs for just Python. Of course, we had an option to maybe do some keyword detection, natural language processing to parse the actual outline to give them some structure, but we thought, let's not risk giving them too much as to take away the opportunity for them to practice something. So we just do the function stubs, And it generates, like I said, a complete suite they can run right away after they are finished with the process generation. So again, I have a demo here. So this is actual student submission for the word search project. So we have some examples of these words stored in a puzzle or a 2D list of characters. But there is a mistake, so we'll see what happens. Okay. So you can, it says I'm on actually Unix server. You can run the DrCOP by typing DrCOP in my directory with the input file named oil_py, in this case funcs.oil_py. And then because there was a mistake, it gives you some errors. But these errors, as it says, is ignorable, meaning that the tool did its best to reconcile it so that if you don't want to care about what mistake you made, you can move on. But if we decide to fix it, we can go, and it told you exactly where the error was occurring with that arrow, so the student can go fix it and then run it again. And then it's going to give an opportunity to not overwrite the test, something you have already written, and we, in this case, decide to overwrite it. And then we can take a look at what it generated. So this is the function step that was generated. Sorry, it's not color-coded, but you can see the function definitions. Actual DRaCO artifact and the code outline is still part of the file that was generated so that students can still see it and use it while they're programming. And once they're done with writing this, they will see it as a documentation. And this is a unit test suite. You can see that this is a fully populated unit test file. And then students can run unit test right away, and of course, initially it's going to fail because you only have the stubs. Okay. So that's a quick demo of the DrCOP. And then once students have kind of gone through this process and generated an artifact they're happy to turn in, we go into the peer review process, and the first step is actually the pre-screening. What that means is that I'm going to collect all their work, and I'm going to review them and fix some small errors that will cause distractions during the review. So once that's done, I'm going to generate the PDF file from their artifacts, and then it's going to get printed out and redistributed among students. So this is, again, an example of what the student might have written in their function outline, but once it's been converted, it looks a little nicer in a table format with some keyword syntax in there, and we have the bullet point outline with sufficient space for students, reviewer students, to actually annotate the outline. So the informal peer review sessions were, like it suggests, it was very informal. We just gave the DRaCO artifacts PDFs to students and said, hey, you guys, why don't you take a look at each other's thing, ask questions, see if you can make some critiques, constructive criticisms, and students can just review and critique at their own pace. That's what was good about them. And we observed the students discussing some challenging algorithms. Some programs that we used this informal process was particularly challenging, and students were not afraid to just kind of get together, talk about some challenging algorithms, different approaches. So small groups of students. Okay. And in-depth, like the one I've shown before with the worksheet, it's a particular pinpointed questions are asked, and it has implementation of certain features and corner cases, so students are more directed towards those. So it, of course, like I said before, it encourages comparative analysis. Ask students, okay, what have they done versus what you have done? How are they different, or how are they similar? So students are more focused on completing the worksheet, kind of like a homework they need to finish. So there were less communication between the students, but we observed that there were more pinpointed questions. There are opportunities for certain students to realize, oh, that was a corner case I was missing, or, oh, that's something I didn't think about, or if it is there, but it's kind of hard to read for other people. Okay. So here's another quick example, a different worksheet. There were some cases we just made it simple, just yes, no, I can't tell kind of questions, so the student can circle it, move on. So again, kind of reading question where they're supposed to identify certain features and where in the implementation plan the features are presented. And some comparative analysis again. It was a design decision that was different, was similar, and then make a suggestion and give it a letter grade. Okay. So in order to do the validation, we got to refine our thesis statement a little bit. So we came up with the two hypotheses, null and an alternative. So null hypothesis says using of our DRaCO-based pedagogy does not generate any difference or worsens the beginning students' performance on exam questions that test their ability to program. And the alternate hypothesis, so this is what we want to see if our method was effective, states that our method, or DRaCO-based pedagogy, does generate improvement in students' performance on exam questions that test their ability to program. So in order to collect the data to do the statistical test, we have set this score, it's called the Ability to Program, or ATP score. And it's just based on some midterm exam problems and lab final exam scores that were designed specifically to test the ATP. So in the interest of time, I'll just quickly flash you this table of what problems were involved in the exam and why we designed or chosen those problems to be part of our evaluation of ATP. So we start with something simple, and then in the lab final and also in the later exams, we test a lot of different components of the ability to program, because early on it's kind of difficult for students to kind of express their ability to program in certain things, but later on, towards the end of the course, we expect them to have learned sufficiently to be able to do well on some problems. Okay, so that's what it was, and then this is what it looks like for a single student. So we put together all these scores and their weighted means, meaning that each score they earned for a problem is going to weight it based on how much they contribute to the course, overall course grade. So we got scores from midterm 1, midterm 2, and then lab final. It has some different components to it. And then in this particular student's case, got 76 out of 100, and this score is 13.15% of the student's course score. And this is a distribution between the experimental group and a control group. So the experimental group being presented in this narrower red curve right here. And we can see that this right here, the experimental group, definitely shows at least slightly higher mean. And there are some the lower scores from the control group. So of course, the interpretation of that graph can be pretty subjective. So we'll go ahead and talk about actual statistical test. But before we go there, we talk about friction. So the friction, like I talked about, was just a measure of students' emotional resistance. And it was all based on the student exit interview. So we did one-on-one student-teacher interviews at the very end. And they were based on a Likert scale. A lot of the questions asked students to, hey, rate the statement from agree or strongly agree to strongly disagree 1 through 5. And at the end, there was an open discussion where students could say anything they wanted about the course and how it went. Okay, so that's the empirical study, and let's talk about what we got from that study. So we did a two-sample, a one-tailed, unequal variance or heteroscedastic t-test. That just means the variance between the two samples are not the same. And it was performed only over the composite ATP score, so no other data like friction is involved in there. And so the way we set up our thesis statement, we're testing only for the positive change. So that's why we did the one-tailed. And we set we preset the significance level to be 0.05, meaning we're not gonna later on go and change the significance level to make our experiment look good. We're gonna say if the test says the probability is greater than 0.05, then we cannot make any statistical significance statement. So our data actually came out to be pretty good, but still not enough to be statistically significant with 0.0644. And another thing we looked at is the effect size. So in order to give some context, so this is Co's work, who particularly in education makes use of this particular formula. And he says, if it could be shown in education that making a small and inexpensive change would raise academic achievement by an effect size of even as 0.1, then it should be significant. Of course, our method was it small and inexpensive? That's arguable, but I just wanted to give some context in education what this number means. So our effect size turned out to be 0.5, so that could be classified as medium according to the same article, and that just means that it's large enough to be visible to the naked eye. And as you see, the plot does show some difference that can be identified by naked eye. Okay. All right, so now the friction. So just a reminder that the measure of friction was basically just purely based on the exit interview data, so it wasn't part of any exam or anything. And a couple things, I'm just going to note some notable things that I've seen during the interview, is that we observed some pushback and difficulties from students. They said it was difficult to sometimes deal with the DRaCO, it seemed like a little bit extra work still. And in particular, the Dr. Kopp they're still trying to get used to the Unix command line environment coming from probably exclusively GUI, a lot of them, and having to deal with it, being able to understand the error messages sometimes. That was a little difficult for some students. Still, the numbers show from the Likert scale show that Dr. Kopp is actually a strong motivator. Students said, I would rather have Dr. Kopp than not have it. So the likelihood of students continuing to use DRaCO process was higher if they had something like Dr. Kopp for them. Okay. Some unit tests, the complete unit test suite generated by Dr. Kopp received some positive feedback. Quite a number of students actually said they liked having those unit tests generated for them. The one thing that we noted from the exit interview is that the usefulness of the peer review, the control group had really high expectations. They gave really good scores. Like if we had done something like that, I think it would have been helpful. That's what they said, as opposed to the experimental group who were pretty lukewarm about the whole process helpfulness. Okay. Right. So another thing, and kind of last data analysis we did, is we ran a sentiment analysis on that open comment. So we ran this on a Google Cloud Platform sentiment analysis, and it just analyzes their sentiment just in the final open comment during the interview. And this is the score range they provide. And what we get is a score. So the most negative emotion being -1, positive emotion being +1, and anything in between. And it also gives us an unnormalized magnitude of how much that sentiment showed up in the text. So the experimental group got a score of 0.2, which according to this particular graph just shows up in somewhat neutral range. In the magnitude of 33.9, and if I normalize this just over the number of words they have given me, it becomes 0.02, compared to the control group, which had actually positive with magnitude that is, when normalized, a little higher. So we can definitely say that adding the DRaCO on top of the existing curriculum did generate friction that's observable. Okay, so now with this data, we make this conclusion. So again, as we have implemented it the way we've done it, there are some negative emotional responses from students that can be expected. However, it shows a strong potential in the DRaCO-based pedagogy in generating meaningful improvement in beginning students' ability to program. Again, with the statistical test not being satisfied, we cannot conclude that it made a statistically significant improvement. However, we still saw that it has pretty good potential. A couple things, before we move on, we need to point out is that our validation methods, like the exam problems I've written, I've chosen, I've graded, and I have assigned scores to, didn't conform to any particular standard, so that our particular bias might have been subconscious, caused some shift in some sense. And for the most part, the sample selection was dependent on how students enrolled in the courses. So we did not have any control over it to be able to make it sufficiently random. And of course, this was not a secret experiment. Students all knew what each other section was doing, what they were doing more, what they were doing less. So maybe some students felt negatively enough to kind of bias their own scores. Maybe some students felt positively enough to bias their own particular scores. So with this, I think it definitely calls for a replication study. With this DRaCO workflow, nicely packaged, I think it can be implemented in ways that's perhaps less invasive to the existing curriculum. So replicating the study to see the effectiveness, I think would be really good. And I think it also really calls for more streamlined, better version, pretty much, of Dr. Kopp, so that when students use it, they're not so angry about it by some difficulty they encounter. And in particular, I think if we could port the Dr. Kopp or any of the similar functionality to something that students are more used to, web-based, or something that has at least some graphical interface that students can use more easily with the buttons, and I think that might generate some positive feedback as well. Okay, so sorry if it felt a little rushed because I know that Dr. Jansen is on the clock. But again, thank you, and at this point, I can take some questions if there are any.
That you mentioned earlier, like the blank page syndrome. Was that something that it was kind of allegorical on your part, or was that something that was kind of identified in like maybe some psychology literature? Like, did you get that from some other studies?
Yes, it's by a program by design, which is Dr. Clemens is a part of, and actually the how to design programs and the whole curriculum of Racket that we've seen in some courses here is an implementation of a pedagogy that tries to eliminate the blank page syndrome and guide students into the right direction of designing programs before they code.
Okay.
Yeah.
And on a similar note, the notion of friction, was that something you came up with? Or was
That is something I came up with.
Okay.
Yeah.
Okay, thanks.
Yeah. Thank you. Anything else?
I have a few questions just
Yes.
on your study
Mhm.
design. So how many students were in the study?
There were 34 total, 17 experimental, 17 control.
Okay, so it's
Yep.
just one section and you divided it into
Yes.
2 labs.
Mhm.
Okay. Did the non-DRaCO group
Mhm.
so your control group,
Mhm.
did they have any kind of similar, I mean, what did their handouts look like? Like you gave the instructions.
Mhm.
in
Yeah, so
DRaCO format.
so yes, I can actually, I have that here.
But they had something similar?
Yeah, so I could show it to you as well, and it's on in the appendix of my paper as well. They have exactly same specifications, so project specs are exactly the same, except the instructions on DRaCO portion is missing.
Okay.
Yeah, so they have the same structures on sometimes which functions to write or what the problem statement is, but there's not much of a pointer to you should use certain process to plan out your strategy.
Okay.
Yeah.
Right. And what about peer review? So there's no peer review?
No peer review for the control group.
Right, okay. And then did the students, when they took the exams,
Mhm.
did they have similar forms available to them?
Yeah,
The
so
DRaCO students?
yes, so the exams are same across all students, control and experimental, but just so that we kind of avoid some bias of, oh, I've seen this before versus I've never seen this, I've always provided an exam problem that's almost identical to the ones that's going to show up on the exam, as far as the forms they need to fill in. And also in lecture, I spent some time describing the general procedure of DRaCO, not particularly asking them to do it, but what a design recipe is, what we do when we do outline. So outline was introduced more gently in a sense that every time we needed to write some code on the board to show students, I would always start off with some outline and then fill it in so that students know that that's the process that we take.
For both these?
Yeah. So that was done in the lecture. Yeah, for both.
So maybe I'm confused. So then on the exam, what were they doing? Were they actually writing Python code?
So it depends on students. So exams. Some of them were given the code outline, so fill in the parts of the code outline was one of them. Some involved reading Python code. Some exam problems involved coming up with test cases, just example values, what were the good values to test of Python code. And the lab exam at the very end asked them to write a Python program, and that one was just any other lab exam that's done without DRaCO. Just write this program. And I was testing them not only on correctness, but more heavily on the decomposition on that part.
Right, so that was actually my next big question, was on decomposition at the high level.
Mhm.
So you didn't say very much about that.
Mhm.
How does DRaCO actually help you with that decomposition? Because isn't that the same whether you're using DRaCO or not?
Yes, I think that's a point that can be argued. What DRaCO helps students do is like just with the template, seeing the function template, DRaCO template, so design recipe template and the outlines that needs to be generated. The way we structured it with the project is that we always made the deadline for the DRaCO artifact far in advance of the actual deadline. So students will have to work on the DRaCO portion earlier on, whether they like it or not, so that they would have the decomposition done before they can jump into programming.
And the DRaCO part being both the high-level decomposition as well as the
Yes,
the
yeah, so
detail
the
for
full
each
thing, yep.
function?
Yep, the whole workflow.
The whole
Yes.
thing, okay. And then the control group, did they also have to turn something in early like that?
Not at all.
Okay.
Yeah, they were just given the
affected
spec
that,
and
I mean,
everything
just having an early.
Threat to validity.
Yeah, threat to validity.
Yeah.
Okay.
Yes.
So I understand this workflow that the students in the experiment, they are writing this outline and then doing peer reviews of this outline.
Yes.
And so this assess their exam scores at the end, but what about their project scores? Did those improve?
We did not take the project scores into account, mostly because we certainly looked at the student submissions on DRaCO, and I did examine the student, the project outcomes, but because of the focus here was that how are the practice of, for one, the practice of doing the DRaCO portion and how much students are putting their effort into it, rather than are there projects passing the test cases in a lot of those test cases in CP 101 in particular test for something that has not necessarily to do with the decomposition, but did you match the strings perfectly? or did you test for this particular really odd, the corner case that probably nobody has gotten or almost nobody has gotten. So the focus was definitely to try to look at decomposition process exclusively by asking them to do that on an exam versus looking at just the outcomes, if that makes sense.
So I can see how focusing on the exam questions is in some sense a better question to ask because it's not such a softball. But you would hope that the DRaCO students would in fact maybe do better on the projects, or their code might be better. This is not a formal question. Do you have any impression of the student code, whether or not they did better on the projects, or whether their projects were better organized?
No, I did not. And I think what that depended mostly on is how motivated students are get the higher score, because a lot of the difference came from my observation, is those really, really small test cases, the corner cases, or the string matching. So some students who really, done it, they planned their time right, they cared to get the 100%, did a lot of diff testing at the end and got the strings to match perfectly, versus students who didn't really care for those.
So you're saying the existing testing framework for 101 is badly broken?
I don't think so. I personally don't think so. Because that is necessary, the testing framework that is in, but that does I don't think that alludes to the process I was trying to.
Golly.
Okay. Yeah.
Well, one of the reasons why I was curious about the project scores is because, as we all know, one of the most sensitive things that we have in the lower division courses is the word collaboration.
Yeah.
And so, at what point then does it become collaboration if they're just kind of sharing the structure of their code with one another?
Yeah, no, I totally agree. So in principle, of course, CP101 should be completely non-collaboration, but one exception I gave was during the code review itself, but the sharing of the code itself was not allowed, and we ran actually the anti-plagiarism to see the code sharing, which I found to be kind of irrelevant to what we have done in class.
So you didn't find that, I've seen you use Moss, you didn't find that the output of that was higher for the students in the experimental?
I did not run that particular analysis between the control and experimental. That's something definitely I could look at, but the output I got from Moss didn't kind of lead me that direction where it showed like immediate consequence. Yeah, the consequence was pointing to quite something different.
If you haven't noted which pairs of students were reviewing each other's code,
yeah, actually,
find that
yeah,
more
right, totally. But actually, what I found by Moss, and this is why it didn't even lead me to think about it, is because a lot of students who collaborated were collaborating with someone from the other sections, which had nothing to do with the experiment. So, yeah.
Oh, how many instances of collaboration did
there were a lot. Not in my section. Across the whole 101 who shared the same curriculum. So that was a pain in its own area. Yeah. Yes.
Do you think there's a danger of cross contamination across your two groups, like this, since they are in the same lecture? Would the control group students talk to the experimental group students, and the experimental group students would say, we have to do all this stupid stuff?
Yeah, so I think that's what the students' own bias might come into, is like, they would complain about all the stupid things, and then maybe the control group students felt a little better because of that. So I think there certainly is some cross-contamination because of the students interacting with each other. But in order to just make sure, what I wanted to make sure is that the students who were in the control group didn't use Dr. Cobb or any of the process. So during the one-on-one interview, I asked them, and thankfully all of them did not. None of the control group students used the process from the experiment.
It would have been a good sign if all of them did use it.
Yeah.
So you mentioned your timetables. Okay, fine. I'm just asking. You mentioned that a lot of students found the peer review process to be less helpful than they had expected it to be. If you were doing this again, would you consider running it with reduced or eliminated peer review? I
think what I would like to try is structure the peer review a little better. So instead of having some informal sessions where some students might really engage, but some students might just, maybe they haven't put in a lot of effort, so they don't have a lot to talk about in the DRaCO workflow. I would definitely, give more students to work on the DRaCO and more kind of guidance along the way from the teacher so that they do put in some good amount of work. And two, give those worksheets kind of work with some more reputable sources to make the review process hopefully helpful, and then see how that goes with the structured review that asks pinpointed questions on certain things that
So
students might miss.
you'd like to make some changes to that portion?
Yeah.
of the class.
Yeah.
Okay.
So the students could just like choose their own partner for the peer review process?
I paired them up just to be the person sitting next to them. But in the informal sessions, I did observe that some students like to, if they're sitting close to each other, kind of talk together about the DRaCO artifact.
There's one thing that might
Mhm.
help, and well, you wouldn't know this until after 1 or 2 projects have been submitted, but pairing up
Mm-hmm.
a student that had been performing well up
Yeah.
to one that had been struggling, hoping that
Mhm.
maybe
Yeah.
more than just a peer review, but maybe some kind of
Yes.
peer
Yeah, I think it would,
assistance.
totally like motivational as well in that sense, to have peers help. Yes.
Do you notice any discrepancy creep between the outline and the final program? The outline might be naive and then the final program completely different.
Not as much as I would have thought, and I think that I gotta give credit to the CP 101 project structure that starts with really well structured. Okay, write these functions, and then it moves on to something a little less hand-holdy, and then it moves on to still some open-ended project statements, but still has very obvious decomposition opportunities. And of course, we talked about in class, these are some good strategies to go about. By I think most students abided by that in both outlining and in implementing it. Yeah.
That comment almost leads towards a question of like, would it be better to introduce this in a next class maybe where they're doing more of the decomposition themselves?
Yeah, I think this could certainly continue. Yeah.
Okay.
Yeah. Yes.
Do you think a quarter is long enough to see improvement among the students by using this method? In other words, they're getting better at writing programs. Is the quarter long enough
Mhm.
practice?
Yeah. I think it would be really fascinating to do a little longer and see how students improve. Yes. Anything else? Yes.
I was just wondering, because I know one of the papers you had talked about really motivated the whole looking at the syntax.
Mm-hmm.
When you were doing your literature review of like computer science didactics, is that generally agreed upon, that syntax is like the main issue in computer science education, or are there other issues and this is just something you thought was lacking and you could do better in?
So the shortcomings I've identified are mostly based on my my observation, but the issue that the syntax does box student down is agreed upon by many. I wouldn't say all, but I definitely, while I was doing literature review, there were a lot of attempts. Okay, the syntax is bogging students down. How can we make it easier? How can we make it simpler? Or how can we get rid of it? There were a lot of attempts, and I think the related works I've shown here, it particularly with Scratch, that target younger students is a good attempt at that as well.
Okay.
Yeah.
And are you going to release your tools too? Because it seems like
it is publicly available. Yeah.
Because you're targeting like introductory computer science level at the university level, but I could totally imagine that being used by even high school or below. You know?
Yeah. I think so. Maybe I underestimated the whole K through 12 generation a little bit, but having seen the interactions with students, I think it is feasible. Although I wouldn't necessarily target it to like really young students,
Well,
like
since
elementary
those
school.
fifth graders are so good at picking out the names already.
Yeah, perhaps.
Great.
Okay. Any other questions? I think we're out of time. Okay. Well, thank you.
All right. Thank you.